welcome to the Evolve webinar number 9. My name is Alexander Stocker. I'm from the Virtual Vehicle Research Center, and I'm the organizer of this webinar titled Automotive Data Analytics with Evolve. We have today two talks. One talk is from my colleague Emre Kalaici. It's about the Evolve use case concerned with graph-based data integration for machine learning in automated driving. The second talk is from Konstantinos Xylogiannopoulos from AVL, and Konstantinos will talk about Evolve scalability and performance for automotive data analytics. Just one word about Evolve. So what is Evolve? Evolve is a project funded by the European Commission in the ICT Horizon Europe program. The goal of Evolve is to create a testbed, a platform integrating high performance computing, cloud and big data to support data intensive use cases. There are a lot of use cases from different domains. And today we focus on the automotive domain. So other webinars were targeted on other domains. And the idea of these use cases is to deploy machine learning pipelines, workflows on the Evolve testbed, and also to accelerate computation. Both talks will report about what they did and about their findings and challenges they have been working on. And I think it should be quite interesting also for our participants. Please feel free also to ask questions. So we have, after the second talk, we will have a question and answer session, approximately at 11:15. You can already, if you want, post questions into the chat. So there is a chat symbol. Please use this symbol and just post your questions. And at the end of the talks, we will try to answer them. Okay, that's it for my introduction. I would like to hand over to Emre for the first talk.
Thank you, Alex, for introduction.
Thank you, Emre.
I will share the presentation. Is it visible now or?
Yeah.
Okay, yeah. I'm going to first explain the motivation behind the use case that we did actually, then explain what we did for implementing this use case. So this is a teamwork. I would like to mention that we are 5 people working on that, and I have the honor to present it actually. And we started on this use case on this year June, and we plan to finish until the end of November. So it is kind of actually 5 months use case, so there are still some work ongoing, and I would explain this ongoing work and some possible future paths in the end. So it starts with the preparation of the environment, and then we are currently in the running the experiment phase, and we plan to finish it. So the first motivation is about the change in problem solving, that we see the previous engineer workflow for solving a problem as 0.1 workflow, where engineer deals with a problem, they creates some smaller subtask from that problem, implements the solution, and this solution is executed directly on the car. This is how it is generally in traditional way of solving problems. You just develop an embedded system, and this embedded system just applies the solution. But with the machine learning and the proliferation of the machine learning in the automotive sector, now it is about defining the neural network. So we start to see architects or machine learning engineers trying to define some structure for solving using some neural network or some other kind of machine learning algorithms. And we have some people dealing with data, which are called labeler or annotator, which are checking the images, videos, and somehow labeling them for example, we're considering a detection, object detection, and they just check this image and they try to label everything on this object, because we are going to use this data set for training the machine learning algorithms that structure is defined by a machine learning engineer or some kind of architect. So the question is, can we provide a warehouse that we integrate many different data sets, which are somehow contains many different scenarios in them. So this is the basic idea behind context sense. The context sense is the framework that we try to create a knowledge graph-based data repository, which user systems or anything can query, explore all the data that is available in this data set. So the basic idea behind it is that machine learning approaches are increasing, especially in autonomous driving and driving assistive systems, but they require a lot of computing and a lot of data for corresponding to different scenarios to get really useful and efficient results. And for future autonomous vehicles, we think that we need a powerful data repository and processing pipeline for multimodal data sets. So we need to be able to cover a lot of scenarios in this data set. We need a continuous and scalable growth because data is always changing. You may encounter with new scenarios or with new data, with new problems when you drive your autonomous vehicle. We need a contextual knowledge because sometimes, for example, you need to be aware of your surroundings to find dangerous situations so that car or driving assistance system will act or at least warn the driver in a better way. And we need this ability to execute computational intensive enrichment and model training algorithms, which is high performance computing can help here. And one additional thing that we need to consider is that we need safe and reliable software systems. And because of that, monitoring and understanding the applied techniques and the results are critical. So what we think is that knowledge graph-based data integration plus high performance computing contains lots of promise for machine learning in automated driving. And we built this use case based on this assumption in the beginning. So Alex already somehow summarized what is the Evolve platform. It is an advanced computing platform with lots of high performance computing features and system software somehow adapted to that. It provides an easy deployment access and use in a shared manner with data protection. And it allows us to do some big data processing with lots of or very large data sets. So the main aspects in that manner is that it is scalable. It contains large memory, so we can do many memory consuming and processing consuming tasks easily in it. We can use GPUs, so there is a room for accelerated processing, and it allows fast interconnection. So even nodes are scattered globally or in geographical sense, this fast interconnection allows quick access to data that could be on different nodes in the platform itself. So the first phase is the preparation of the environment. We dealt with this phase in the summer. So we needed first download data set. We are using two publicly available data sets for this use case and our experiments. There is this from Motional company, there is nuScenes data sets, which contains 700 scenes with annotations. So it is around 300 gigabytes data. And we also used Lyft Level 5 perception data set, which contains 350 scenes with annotations, which is a bit more smaller than the other data set. It is around 6 gigabytes. Why would we have chosen these data sets? They are open, they are published with Creative Commons license. We can easily use them in any environment, and they are using the same nuScenes format. So we just uploaded these files to the Evolve platform. You can see the screenshots on the site, which are showing where we put these files, all the contents of these data sets actually. And this is the schema of the nuScenes. This schema is important because when in the next step, we are going to import this data to a knowledge graph, which is going to be a Neo4j graph database. And we are going to create our nodes and relationships based on this schema. So each table corresponds to a JSON file according to schema, and we need to read these JSON files and create corresponding nodes and relationships. The second step is deploying the stack. So we use some external services and we containerize everything. Everything works as Docker containers, and we use some external services. So we needed to create some templates for the Evolve platform because platform already was providing us, for example, PostgreSQL database, but Neo4j, RabbitMQ, Flower, and pgadmin wasn't available on the platform. So in the summer, we prepared such templates to deploy these services. So that was the first step. Then we have 3 containers contained in our context sense framework. Actually, one is the repository, which is for storing application specific data directly to the PostgreSQL database. And we have algorithm execution engine, which is an Apache Celery based asynchronous worker. And we have notebooks, which is a custom image using Jupyter Hub, which provides us somehow a collaborative environment using Jupyter notebooks. And this is the architecture. Notebooks and repository also use some context sense libraries. These libraries allows easy access to the knowledge graph, which is actually a Neo4j graph database, and also allows us some basic deduction algorithms provided from TensorFlow or developed by us or customized by us actually. And algorithm execution engine uses message queue from RabbitMQ to do asynchronous tasks. For example, we can use import process to be run in the night without any need to keep it open using this algorithm execution engine using Apache Celery workers. And this is the services that currently runs on the Evolve platform for this use case. And these Flower pgadmin are generally used for monitoring. Flower helps us to see all Apache Celery worker tasks and their results. And we also have Argo, for example. This Argo is also an external server provided from platform for parallelization tests that we did in the use case. So as I said, the first step, we stored the data sets on the platform, and now we need to create the knowledge graph extraction. And we have some common properties. This is generally used for understanding how these nodes and relations are created, when and how, and based on what kind of input. So these common properties are kind of provenance, tracking the provenance of the data or nodes and relationships that we have. So it is generally, we have an algorithm execution engine property which contains the name of the adapter. For example, these adapters are used for importing data, and we have scope, we have role, we have some unique identifier for each adapter, and we have some timestamp and task ID, user ID, which are specifically for tasks that are run on Celery. And we have all these tables from this nuScenes schema, and we use these tables information. For each table, we just read attributes from JSON file that is corresponds to a table, and create a node query. And we run this node query directly on Neo4j for storing nodes from this JSON file in the knowledge graph. And we repeat that operation also for creating relationships. So we create the relationship queries for each table, for each JSON files we have, and we execute the query. And in the end, we just get a knowledge graph that are created on the Neo4j. You can see on the right the graph schema, which just very similar to the Neo4j schema, because we just use the same schema information just to store it as a graph solution. And in the graph, currently we have 7.5 million nodes with 13 different labels. These are all nodes that we extract from Motional and Lyft datasets, and we have 25.3 million relationships with 5 different types. And here is a subgraph that shows a sensor. That sensor could be a camera or LiDAR, and the calibration of that sensor based on the ego position, based on the car position, and sample data, which contains the file that is created by the sensor, and 10 ego pose, which contains the car position information attached to this sample data. And here is another one, for example, that shows, so we have maps in these data sets. These maps corresponds to the geographical map of the car, where this car driven to create this scenario. We have logs for each map, and this is an example of a scene from a log from a single map. And sample annotations are used for annotating the objects on these scenes, and instances corresponds to the objects that are found on each of these sample annotations, and categories are shows what kind of things are these instances. So here you can see there are two detected types, that these are car and bus. So after importing the data, the next step is the running experiments. And for running experiments and also for adapters that are used for importing, we generally use Jupyter notebooks for reproducibility actually. And for the experiment, we have selected object detection approach actually. So we customized the YOLO version for object detection model. We created a library for that so that we can easily use it with any image. And we also wanted to test with TensorFlow Hub models that are trained on COCO 2017 dataset. So we have selected 3 different models from TensorFlow Hub with different architectures and with different backbones, just to have kind of a set of various approaches, various different methods from the literature actually. So we prepared different notebooks for running these object detection experiments. As I said, we really care about reproducibility, so we can run these notebooks in any environment that supports Jupyter, that contains a Jupyter server. So this means that we run them on local machine, on our virtual machine, which deploys everything in a and then we also use on Evolve platform. So this is an iterative process. We implementing the notebooks and improving the process and understanding the bottlenecks and trying to improve the libraries, and also the detection usage is kind of iterative process which happened in the last months in this use case. So we use context sense library using graph access to directly contact to the knowledge graph, and we use detector library from common functionality to integrate into any workflow actually. So how these notebooks are run, they retrieve sample data nodes which contains file paths to the images, for example, from knowledge graph, and then for each node which corresponds to a different image, it reads the file from the data set from the platform itself and applies object detection, and detection results are collected to save the results in the end directly to knowledge graph. Let me show some examples. This is, for example, YOLO version 4, where you can see 7 cars and 4 traffic lights are detected in this example. When we run CenterNet with our Hourglass backbone, now we can see 13 cars, 6 traffic lights, and 1 truck. So it is easy to compare also different object detection algorithms with finding these results. But we, for example, on efficient DAT D0, we have a bit worse results than YOLO version 4. Only 6 cars and 2 traffic lights are visible here. And on faster RCNN ResNet, we have some wrongly detected people on the right also. These are actually bins probably, and they are just detected like persons. So, but otherwise 8 cars, 3 traffic lights are correctly detected here. So it seems to us that CenterNet for this image is really doing a good detection. So finding such results allows also users to compare based on the images also this result. What we do is, after detecting a result, we just enrich the knowledge graph by adding the result confidence, the prediction time, how long it takes to predict results, and the bounding boxes of the objects that are found with a relationship to the category that we detect. Here you can see that 2 detection results for the same sample data. 2 cars are detected for the same sample data, which are attached to car node. And we have 5 different categories listed here. These blue small boxes corresponds to sample data. So for example, some of them have cars, bus, and traffic lights all together. And here all the labels, all the different objects, categories that are available in the graph after running for example, YOLO version 4 detection algorithm. So one thing here that running this parallel is another experiment that we want to do, because it really takes long to run it sequentially. So we use Argo workflow parallelization. It is taking around 20 minutes for 1,000 images running this detection algorithm. If we compare it with our local runs, for example, optimized sequential running of 1,000 image takes around 67 minutes in our development local laptop and 46 minutes in our virtual machine, which uses containers actually. So we have almost 2 times improvement using the Evolve platform with the parallelization. So based on this use case, what are the benefits that we got, or what are conclusions? So with the context sense libraries and context sense framework, we aim to simplify the access to the data through a single unified layer, so that anybody who needs some kind of scenes can directly access to these scenes information, to the sample data containing files, and can run some machine learning algorithms on the files that are retrieved from it. And users can extract, enrich, explore data using the knowledge graph easily through navigating the graph itself. And through Evolve, what are the benefits of Evolve for us is that data sets are stored on fast storage. We weren't able to store all these almost 350 gigabytes on our local computers, and Evolve helped us to overcome this problem. And it was really easy to deploy context sense stack on the Evolve platform, and helped us to test this parallelization in an easy and efficient way. So why we are storing the detection results are for these reasons. So additional data put into the knowledge graphs can help us to compare all the methods that we are using, applying, and we can also use these results as ground truth for training additional algorithms, and allows us historically checking the results. So comparing the versions of the same detection algorithm, for example, and understanding if improvement really changing something, or what are the results of the improvement, and allows us to keep track of the source of these results, so that we can understand if a node is created from a specific detection or not. And what we are currently doing, we are trying to improve the Argo parallelization, because there is some improvement possibilities. We didn't do much about improving the performance of each run. And we are also investigating some model training approaches, because we already trained models for the object detection, but we are also want to test if we can use some kind of transfer learning using the images that are available in a knowledge graph. And also we want to investigate fifth shot learning, which is the new improved machine learning approach that is somehow getting an increased popularity. And also another thing that we want to test is the rule-based systems for enrichment. For example, we want to test, this is going to be in November generally, we want to test if we can use some kind of ontologies for finding, for example, or applying different rules and finding some results based on these rules. So this is what we did in the use case. And if you have any questions, I will be happy to answer them after the presentations, I guess.
Thank you very much, Emre. Thanks a lot. Thanks for your interesting talk. Well, as you said, there will be time for questions after both presentations. So please, everybody, if you have questions, just write them into the chat. So the next talk is from Konstantinos from AVL. Konstantinos.
Hello everybody. Hello. Here, let me share my screen. Can you see my screen? Everything okay?
I can see your screen. Looks fine.
Okay, great. So I'm Konstantinos Klianopoulos, I'm a computer scientist, and my position is as a data scientist here at AVL at the Business Intelligence Department. Our project was to check evolve scalability and performance for automotive data analytics. In order to do this, we try to do some pattern detection, to apply some pattern detection and data analytics tools that we have built. So practically, when we're talking about an engine, we have a deterministic system. It should perform in a very reliable and stable way. As you can see here, we have some signals from different sensors. Everything looks to have a specific time interval, period, a specific cycle. So in every case, we can detect what we call here normal patterns for every channels. At some point, although there are cases where an anomaly can occur, and this could lead to an engine failure, actually catastrophic failure, which if we are talking especially for large engines, for large vessels, it could mean millions. Now, in order to monitor these signals, because we use, as I said, many sensors, but we don't care only about the measurements. We care about the health status of the sensors, because there are cases where we may got not properly recorded values from the sensor for the signals, which may look okay, which actually they are not, and this could lead also to problems. So we have an example here from a cylinder pressure sensor. So we can see here the blue line is what we call the reference line. So the normal behavior of the engine. For some reason, as we can see, the sensor can record everything almost fine, except at probably in the mid of the y-axis where it stops approximately in the middle, it gets flat and then goes back down. So if we aggregate this and we take a normalized signal as we usually do, we can see something that looks like this bell curve, let's say, signal curve, but which simulates very well the normal behavior, but actually it's not normal. And the problem is not here with the engine, the problem is with the sensor, which we should be able to detect that it has a problem and should be changed in order to avoid missing important information in the future. In order to do this, we have this EPOS system. It's a very sophisticated system that we use to monitor all the signals coming from the sensor of the engine. That, as we can see down here, we have also this sensor failure, which it's actually a very important part of the system. So the whole process is a little bit complicated. We have many different types of raw data in many different file formats. Usually automotive industry use its own standards, and this complicates, as we will see later, the things a lot. So we have to get this information, these files converted. We have to do several kind of statistical or mathematical parameterization, normalization, execute and find some aggregates or other kinds of information, and of course present this in at the end with some kind of a visual, like in the EPOS system, or save the reports in a more meaningful way. So in our case, this EPOS system, it's based on the Concerto software from AVL, and it's a Windows-based application. So the overall execution process for the sensor analytics is that we have to read and pre-process the data. For this reason, we use this iFile Manager component and Win32com that are allow us to read this specific binary files that the raw values have been recorded. This unfortunately is only available for Windows and cause some kind of problems, we'll see. So then we perform our cylinder analysis, which because of the complexity of the system, right now we can do it on our workstations only sequentially. So if we have more than, not if, of course, we have more than one cylinders, and every cylinder has to be analyzed one after the other because of the complexity of the process. Then we, of course, we report the engine status and we write the results back to the database. So this is the how the system is currently working. Now, of course, we got this excellent opportunity to test everything on the Evolve High Performance Computing Platform. Huge system, a lot of technologies. It's based on a Linux system. We have to use a lot of Python and other systems, try to utilize all the nodes, cores, GPUs, FPGAs, whatever is available from this platform. So the project's objectives for us is to implement the ecosystem or the sensor failure part of the ecosystem on the Evolve platform. So first of all, we had to convert the EPOS prototype to a Linux-based application because of these dependencies we have with Windows libraries because of the automotive file standards. The next step is to use Docker to create containers and upload to Evolve HPC to execute. And the most important part from, let's say, performance perspective is to use this Argo programming language with a YAML to try to execute the full process in the most fully parallelized way possible and avoid this sequential execution that unfortunately we have to follow right now. So the new schema, the new implementation was to avoid all this, of course, raw data files and rich direct CSV files, text files. We have, of course, to create our Python code for Linux, for Ubuntu distribution, create the Dockers, upload everything, the containers, and use Argo to execute this in parallel, perform the analysis, and get back our results to Zeppelin notebooks. So one thing for Evolve, graphical user interface to control the operations. So after we have built the system, we use this Argo workflows to build different workflows, different execution pipelines, and to check the performance of the system. One thing that was really great with Argo is that it was possible to parallelize fully everything. So for a very large engine, which is even beyond the automotive industry, we're talking about large engines for vessels with 20-cylinder engines, it was possible to parallelize all cylinders and have the process executed simultaneously for every cylinder of the engine and get back the results from this analysis with using Argo. So this is the workflow execution time from Argo for the specific example of 20-cylinder. There is, as we can see, there is some kind of not evenly distributed times. This has to do with how good or bad the sensors perform on its cylinder. It's not. It is something expected. So for the last 2, 4, or 6 cylinders executed, they start a little bit later. Okay, this has to do also with how the containers and the Kubernetes starts all the containers on the platform. But depending on series of the problems and the execution of the data analytics to detect the problems, the probable problems of the sensors may take a little bit longer. So all these reports, all the results can be and have been reported on using these Zeppelin notebooks. Of course, we have some graph also, but it's much easier to get a full report per cylinder or for all cylinders all together. And actually, we can identify from the system exactly what kind of problem occurred at specific cycles or in the specific cylinder. Now, as we can observe, this is probably the most important graph of all regarding the performance. The Evolve HPC performance, if we take it as per cylinder execution time, actually it's a little bit worse than our current workstation. This is also something expected because the system has to upload the containers, start the system, start the operating system, the Linux container, and start executing the code, which is it's an overhead for the system. However, the fact that it's possible for us to parallelize practically everything means that the execution time for the full legend, not per cylinder, but analyzing all cylinders, it's actually equal to the worst cylinder case. So as we can observe here, these values are practically the same, and we are done. While if we have to go and use the standard sequential workstation approach, it's actually this is a multiplier by the number of cylinders will make this extremely slow. Now imagine that we have multiple cells, and if we have to do this in a real-time basis, because it's very important to continuously monitoring the condition of the sensors, it makes things very difficult. Practically, it's very difficult, close to not possible to do it. With the Evolve platform and the possibility to have everything in full parallel execution, it's something that can be done. It was a very nice outcome from our project. So let's say the conclusions, the output from this project on Evolve, high performance computing in general, and of course, because of this Evolve, it can be extremely useful if we have to use scaled up applications, and applications that can use full scale parallelization. Equally important should be computationally intensive processes, and of course, in every case, we have the data volume intensive analytics to perform. Of course, for cases that the processes are rather small and we have optimized code and it's not possible to do any parallelization, that was for another use case that we tried also before. It's not very efficient because of the overhead that we have from the containers and the defining the node the execution per node from the system. But the final outcome for the EPOS system was very good. Actually, it was exceptional. We managed to fully parallelize the process and get the best results in the best possible time, or close to real time. So this from me. Thank you very much. If you have any questions, I will be glad also to answer everything.
Thank you very much, Konstantinos, for your talk. Mm-hmm. So we have some time for questions. Let me have a look in the chat. I think there is no question so far. Maybe people need a few minutes to formulate one. So please, if you have a question, feel free to write it in the chat. You have seen two different talks of two use cases which have been deployed on the Evolve platform. The first was on automated driving and object detection, using also graph databases to prepare the data, and then running machine learning models and comparing the detection accuracy of objects on images. That was also parallelized and deployed to Evolve to show performance benefits. There's still ongoing work, so we will see a lot more in the next month when the project is closed. And the second use case was about engine test data and identifying anomalies in engine behavior with respect to ship engines that have many cylinders, where parallelization of the data processing makes much sense. And also here you have seen performance benefits using the Evolve platform. So far, I have not seen any questions. Then maybe let me ask one question to Emre. Emre, you have talked a little bit about your future plans on the Evolve platform. What do you think? What will be one of the next steps that you will do?
Yeah, what is currently we are investigating is also important, because we didn't train any algorithms yet on the Evolve platform, which we seem it would be very efficient to use such parallelization capabilities of the platform, because it is generally the training that takes long times for such tasks at hand, and ability to train our own custom models would be benefit, because we understand that different models that are already trained with some different data sets may not fit very well, as we have seen in the examples, to the scenarios that we have. One thing is that we want to train, kind of do some transfer learning or use some current approaches for model training using the Evolve platform, because it provides us a lot of images that we can train our algorithms, and also the annotations that we can compare the results to understand how successful, how much accuracy that we get with our training. And the second thing that we want to investigate is actually these kind of additional approaches, because we have the enrichment capabilities. So for example, we can use some kind of open APIs to include additional nodes like the weather, or like the interesting point of interest around the car, and then based on this doing some rule-based inference over different scenarios, because this is also using kind of rule-based systems is also could be a complement to the machine learning algorithms for improving the performance of autonomous driving, or at least the driving assistance systems, in our opinion. So these two directions is something that we want to actually continue investigating.
Thanks a lot, Emre. Looking forward to see this stuff in the future.
Yes,
maybe also one question to Konstantinos, because I have not seen there's any question being posted. So it seems to be everything was pretty clear, and I'm the only one asking questions. Konstantinos, maybe just one question. I mean, that was very interesting what you have shown. Thanks a lot for that. I'm just interested. I mean, how many? If you can say something about engine data. So are there many engines that show this kind of misbehaviors in ships? So is this some kind of general phenomenon that is to be observed, or is this just from engines that are really then, after they show this behavior, are also not working anymore, at least the cylinders?
Yeah, it's not only about large engines in vessels. We use the same technology also for in cars, and actually this could be also, it's a much larger problem, because we usually want to monitor fleets of cars. So you don't have one engine with many cylinders. You may have an engine with 4 or 6 cylinders, but you may have 100 cars. So it makes this problem even larger, even more complicated. So this kind of problems usually, the specific module is about analyzing and detecting abnormalities in the sensors, not the engines per se. So based on the recordings we get from the engines, we can understand if the sensor behaves normally. And this is very important, because if the sensors the sensor fails for any reason and gives good results, gives us good signals where there is an actual problem with the engine, which is actually very rare, we can lose the engine. Having problems with the sensor is something more normal. You know, whenever you go your car to a test bed for maintenance, usually you have to change a few things or maybe some kind of electronics. It's not possible to change the full engine because something is not working well. So from sensor perspective, we could say that it is normal and it is expected, and yeah, we may have several cases where the sensor fails before, let's say, the standard time to replace it. So it could be that every 12 months or 34 months we have to change the sensor, but it starts misbehave earlier, and we have to detect this. From the engine perspective, no, I couldn't say that this is something that happens a lot. It's a very rare phenomenon, but it's absolutely fundamental to detect it to avoid any catastrophic failure of the engine.
Thank you very much for clarifying that. So there was some misunderstanding also on my side.
No.
Thanks a lot for that.
Okay.
Well, I don't see any questions. So I would like to close the webinar. I thank you very much to both speakers, Emre and Konstantinos, and thanks also to Loba for hosting the Zoom webinar. Feel free to also visit the Evolve project website for more information also on the other use cases. And thanks for your participation. And I wish you a nice lunchtime.
Okay.
Bye.
Thank you, everybody. Bye.
Thank you.
Bye.
Thank you very much.